Hello everyone. In this video we'll be discussing solving recurrence relations. And let's first recall what a recurrence relation is. It's just an equation relating different terms of a sequence for any given index n. So for example, the Fibonacci sequence had the recurrence relation that any given term is a sum of its previous two terms. So you'd have something like, I think we use f sub n to describe that, f for Fibonacci. So something like fn is equal to fn minus 1 plus fn minus 2. So this is exactly what I mean by relating terms of the sequence for a given value n. So that's an example of a recurrence relation. Now, the types that we'll be solving, you'll need actually a recurrence relation and one or more initial conditions. So like here we see a1 equals 3 as an initial condition for this recurrence relation. Before we move on to that example though, I want to take a look at this example where we're given the sequence, but we want to build some type of recurrence relation, and then maybe we can talk about some initial conditions, and that'll actually give you a way to generate this sequence. So let's take a look. Now, 1, 5, 17, 53, 161, and 485, they don't really appear to have anything in common at first glance. So what I'm going to do, and I think it's a really kind of obvious idea at this point that you can do to always get a good idea of what's going on, is to take the successive difference. So let's do that here. So the difference of these numbers are going to be, let's see, maybe it gives us an idea what's going on, but let's see, 5 minus 1 is 4, 17 minus 5 is 12, 53 minus 17, that ends in a 6, I think, so it's going to be 36, good. And then what's this? This is, let's see, 161 minus 53, that's going to be 108. And then that minus that is going to be, well, at this point I can kind of guess. So if you look here, it looks like this is just the previous term times 3. So if I multiply this by 3, I get 324. And yeah, it turns out if you add 324 to 161, you indeed get that 485. By the way, this arrow is supposed to point here, but you get the idea. So this is our sequence of differences. Now what this kind of does, it gives us kind of some hope. If you keep trying to take the difference, then that may lead to something, it may not lead to, I don't think it'll actually lead to anything. What I'm going to notice is that these are multiples of 3, right? You multiply the previous one by 3 to get the next one. So in other words, this actually follows the relation a sub n is equal to 3 times a sub n minus 1. So there are multiples of 3, more specifically, each term is the previous term multiplied by 3. So you multiply this by 3, multiply that by 3, multiply that by 3, and so on. So in fact, this is really geometric. So perhaps the previous one is actually geometric as well. Now I know it's not really geometric because 1 times 5 is 5, and 5 times 5 is not that. But let's do this. Let's multiply each of these terms, the previous term, by 3, and let's see what we get. I need some space here, so I'm going to erase this. But again, taking the difference of the sequence, finding the sequence of the differences really, allows us to see some type of connection that we have 3 times the previous term. So let's take a look at what happens when you multiply the previous term by 3. So a1 times 3 is equal to 3. Okay. 5 times 3 is equal to 15. And then 17 times 3 is equal to 51. Okay. 53 times 3 is equal to 159. 161 times 3 is equal to, that's going to be 3, I guess, 483. And then 485 times 3 is whatever that guy is. So I guess I could do it real quick. So that's 1200, 240, and 15. So that's a 1455. Sorry for the sloppiness there. That actually doesn't matter because we don't even know what the next term in the sequence is. So that was a little bit of a waste of time. But what you notice here is the values we get, 3, 15, 51, 59, 159, and 485, almost match exactly these terms here. Just like that. Only they're off by 2. So in fact, what we have basically found out is a sub 1 is the previous term times 3 added to 2. And we can check this. 3 times 1 is 3 plus 2 is 5. 5 times 3 is 15 plus 2 is 17. That times 3 is 51 plus 2 is that. That times 3 is 159, plus 2 is that, and then that term now times 3 is this, plus 2 is that one. So this is indeed our recurrence relation, and we can use the fact that A, and again, it depends what you want to plug in, but if we start with 0, for example, we could say A0 is equal to 1. So this right here will give us a way to generate this sequence based on this recurrence relation and that initial condition. Fantastic. And now for this next example, we want to actually check that this closed form is a solution to this recurrence relation with that initial condition. Initial condition is really easy to check. Notice when n is equal to 1, A1 is 2 to the 1 plus 1, which is 3, so that checks out. I'm just going to put a check mark next to this. But now, how do we check that this actually satisfies this recurrence relation? Well, notice A sub n is just merely 2n plus 1, 2 to the n plus 1. Okay, now 2 times A sub n minus 1 is replacing n with n minus 1. So this A sub n will allow us to replace that n with an n minus 1. And that right there, 2 to the n minus 1 plus 1, that's A sub n minus 1. And then minus 1. So I'm just kind of mimicking this, but the A sub n minus 1 part is exactly this, replacing this with an n minus 1 instead of an n, using that. Okay. Now, is this satisfied? Well, we can check by distribution. If you add the powers here, you get just 1 plus n minus 1, which is 2 to the n, plus 2 minus 1. That is indeed the same as 2 to the n plus 1. So in fact, yes, we have checked that it is indeed a solution. So now we're going to go on to actually find some solutions. We know how to check if it's a solution now, but now we'll see some techniques on how to actually find a solution. In other words, a closed form for a sequence for a given recurrence relation. All right, so here we have this recurrence relation we're trying to solve with this given initial condition. I'm actually going to try to attempt to show two different techniques. So one is known as telescoping, the other one is called iteration. Now, I'm pretty sure we discussed telescoping in the past. Basically, you add kind of equations in certain ways so that some of the terms cancel out. We'll kind of see that. And iteration is when you basically apply the equation over and over and over and over and over again and notice a pattern in that sequence. So let's take a look here for telescoping. If you actually just get a feel for it by actually writing down the sequence, notice A0 is 4, and then the next term is going to be the previous one added to n. So this is A0, then this is A1, so we're going to add 1 to the previous term, add 2 to the previous term, add 3 to the previous term, add 4 to the previous term. That's really what this says. And notice, again, taking the difference of these, we get 1, 2, 3, and 4. Aha. So what we found out is something we kind of already knew. If you kind of imagine rewriting this, n is equal to a sub n minus the previous a sub n minus 1 term. In fact, specifically here, since this is a0, a1, a2, a3, and so on, we can actually write it out off to the side here. a1 minus a0 is equal to 4. Okay. a2 minus a1, I'm sorry, a1 minus a0 is not 2, it's 1, my mistake. a2 minus a1 is that difference 2. a3 minus a2 is equal to 3. There we go. And then a4 minus a3 is equal to 4. And this actually continues. And notice the first subscript is equal to the number itself in the difference. So we go all the way down to a sub n. That minus a sub n minus 1 is going to give you the number n. And again, we knew that because that's actually a rewording of the recurrent relation. But what's great here is that when you add these things together, you indeed get this telescoping where these cancel out, every in-between term cancels out until you get this, which is really just an minus a0, let me write that over here, is equal to this sum. And in fact, we know what this sum is. That's a sum from k equals 1 to n of just k. We know that's the triangular numbers, n times n plus 1 all over 2. We've seen that before. We know this is 4, so we can add that to the other side, and that's our initial condition. So adding that 4 to the other side, we get this closed form finally for n, for a sub n. Great. Using telescoping. So it's pretty neat to see that. But now what I want to do is try iteration. Iteration is way different. This honestly I think is a little too clever because it's hard to tell when this is applicable, but it's definitely something you can kind of think about. Really, you want to have some relation, recurrence relation, that involves the differences between consecutive terms. That's really when it seems most beneficial to use. But here let's try iteration. So what is iteration exactly? So we're going to apply this to A1. So A1 is equal to A0 plus 1. Then we'll apply this rule to A1, so we're going to iterate. So A2 is equal to A1 plus 2, but just to kind of like explain, so that's using this, when n is equal to 2, you get A2 is equal to A1 plus 2, so that's me writing this. But iterating is, I'm applying the rule again, but I want to kind of plug this in. So I'm going to get A2 in terms of A0. So this is really A0 plus A1, then plus A2, if that makes sense. Now for A3, I'm going to try to grab the previous term like this, okay, and then add 3 to that. See that? So then continuing, we see that A sub n is just A sub 0 added to 1, added to 2, added to 3, all the way up to itself n. In fact, here you don't even really need the parentheses. It's just kind of help to see where we're at and to kind of see how many layers of the rule we've applied. And we know this is exactly n times n minus, or n times n plus 1 over 2. We know this is exactly 4. So we get the same answer, a sub n is equal to 4, plus n times n plus 1 all over 2. And you can check that this is a solution to the recurrence relation like we did in the previous example from the previous board. You can also use this to kind of check to see that it works with all of these terms in the sequence we have so far as well. So just at random, I'll pick n is equal to 4, we should get 14. So we have 4 times 5, it's 20 over 2 is 10, plus 4 is indeed 14. So there we go. All right, so now I think we're going to take a look at one that's a little more complicated using iteration, and then we'll look at one last technique, which is a pretty powerful one that will actually even apply to the Fibonacci numbers. So we'll see that right now. All right, so like I said, we're going to take a look at this kind of more complicated example using the previous technique we saw of iteration. So let's just begin. We're going to find A1 by plugging A0 into this. So that's going to be 3 times A0 plus 2. Iterating, we get A2 is equal to 3 times the previous term plus 2. A3, this is where things kind of get look a little weird. 3 times that previous term, which is this entire above thing, that guy, plus 2. Okay, so it's going to be a lot hard, like pretty hard here to actually see what's happening in general. Like if you go down all the way to the nth one, there's too much happening. You can kind of see what's happening. You have like 3 3s and 3 2s. So a sub n is pretty obviously going to be 3 3s like this multiplied, or not 3 3s, but n 3s multiplied. Something like that. So there's n of those 3s. And then plus 2 plus dot 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 with parentheses plus 2, so that there's n many of those 2s as well. So that doesn't actually help us too much though. I think maybe a better idea is to actually simplify as we go along, perhaps. That still is going to look a little wacky, but let's try to do it and kind of keep track of things as best we can as we go along. So the first one I'm fine with. This one, if we distribute the 3, we get 3 squared A naught, or A0, plus 2 times 3 plus 2. I'll just leave it like that, I guess. So it's a polynomial in 3, basically, is what I'm noticing. Here, well, I guess we're multiplying that by 3. So let's just actually plug that in here. So that's 3 squared A naught plus 2 times 3 plus 2. Distributing 3 here, we get 3 cubed A0 plus 2 times 3 squared plus 2 times 3, and then plus 2. Okay, so it's kind of making a little bit of sense that what this is looking like is basically we have A0 in front multiplied by 3 to the whatever index we're at, And the rest of the coefficients will be 2 multiplied by descending powers of 3. That's what it looks like. So I'll just check one more. A4 is 3 times the previous thing, which I'll just distribute 3 into, if you don't mind. So the powers just increase by 1. And then we add 2 to that. There we go. So, okay. So now I have a really good idea as far as what AN looks like. AN is going to be 3 to the n times A0 plus 3 to the n minus 1 times 2 plus 3 to the n minus 2 times 2 plus all the way down to 3 to the second times 2 plus 3 to the 1 times 2 plus 3 to the 0 times 2, basically. And this last part is great because we actually know this is just a geometric sum. Now, if you don't remember geometric sums, we had actually a closed form for those. So the sum from, let's see, we're going from k equals 0, because we have 3 to the 0 technically, all the way up to n minus 1 of 3 to the k. Of course, each of these are multiplied by 2 as well, so I guess I could write it times 2. But the 2 we can pull out of the sum because it's like distribution. Right? These all have 2 in common, you can factor that out. And now the closed form we had for this, if you don't remember, is that it is 1 minus 3 to the last power plus 1, which is 3 to the n, over 1 minus 3, 1 minus the ratio. In fact, let me just make sure that that was the case, because we're starting at 0 here. Does it make a difference? Just to play it safe, now, you know what? It actually totally works. But just to play it safe, just so I'm not like super unsure of myself, I'm going to actually test this real quick. So let's say n is equal to 4. So that's 1 plus 3 plus 9 plus 27. That's when n is equal to 4 because we're going up to n minus 1, or 4 minus 1, which is 3. And 3 to the 3 is 27, of course. So if you add these two, you get 30. And add these two, you get 10, so the whole thing is 40. Now when you plug n equals 4 into this, you get 1 minus 81 over negative 2. That's negative 80 over negative 2, which is indeed 40. So I'm pretty convinced now that that was indeed the formula. I just didn't remember it right off the top of my head, but I guess I kind of did actually. Anyways, what's interesting to notice is this is negative 2. So we can actually cancel 2 with this. So we actually get that over negative 1, or negative that. Distributing the negative, we get 3n minus 1. So really, we have a sub n is equal to, a0 by the way is 1, so I could have written that the entire time, plus this entire thing, which just ended up being 3 to the n minus 1. And that's nice because these two now combine to 2 times that. So we have altogether a sub n is equal to 2 times 3 to the n, then minus 1. Can we check it? Let's pick a random, oh, we don't have the sequence, do we? I guess we could check that it satisfies that. Like if you multiply this by 3, like 2 times 3 to the n minus 1, multiply that by 3, and then add 2, you get, distributing, we get 2 times 3 to the n minus 3 plus 2, and that's, in total, that's negative 1. So you get back the original a sub n. So I checked the work just by checking its solution to the recurrence relation. And of course, when n is equal to 0, a0 is 2 times 3 to the 0, which is 2 times 1 is 2, minus 1 is 1 indeed. So that was a pretty quick check. Now we can move on to this next very powerful technique. All right, so here unfortunately I don't have any space for an example, but I can at least explain the technique here. So this is known as characteristic roots. And given a recurrence relation that involves basically relating a term to its previous 2 terms, usually what is given is something like this. A sub n is equal to something times a n minus 1 plus something else times a sub n minus 2. So here these somethings are just called alpha beta, or I guess in this case really they're negative alpha, negative beta, because if you subtract, or I guess add those to this side, you end up getting this guy. So whatever your relation is, as long as it's a sub n equals some linear combination of a sub n minus 1 and a sub n minus 2, then you can rewrite it like this so that all of those a sub n minus 1 and n minus 2 terms are on one side of zeros and the other. Then the following is true. You have this so-called characteristic equation given by x squared plus alpha x plus beta. Okay, notice the location of alpha and beta here and here. So we have x squared, x, and constant terms basically with those coefficients, with a leading coefficient 1 here. And the following, this is like the big step, this is just setup. If R1 and R2 are distinct roots to this above equation, so solutions to that equation, which you can find by quadratic formula or factoring or what have you, then the solution, the closed form that is to the recurrence relation, is given by this. A sub n is equal to something times R1 to the n plus something times R2 to the n. So basically, you grab your solutions, you take them each to the nth power, and you have some linear combination of those. Now, when I say linear combination, I mean it's a constant times 1 plus another constant times the other. Alpha and beta are given in the problem. A and B you'll actually have to find, so those are constants that are determined by the initial conditions. So assuming we have at least 2 initial conditions, we can for sure find A and B. Now this actually is an alternative scenario. So that's if R1 and R2 are distinct, meaning they're different solutions, then this is true. But if they're not different, if they're the same, then you basically have the same thing, only the second one needs to be multiplied by n. And that makes sense because since R1 is equal to R2, replacing R2 with R1, this is just a constant times R1 to the n plus another constant times R1 to the n. You can combine those into a single term. But if you multiply the second term by n, you have 2 different terms actually that cannot be combined. Now the reason why this works and kind of where this comes from is because if you were to iterate a specific recurrence relation like this, involving, term is equal to a linear combination of its previous 2 terms, what you'll end up finding is that through the iteration process, the terms almost look geometric. So almost like you are having some constant to a power appear each time. And it makes sense because you're going to be multiplying, in this case, you'd be multiplying by alpha and then adding to multiply by beta. So it's almost like you have terms that constant powers appear. Kind of like in the previous problem, we had 3 to the n appear with each thing that looked very geometric. We'll have something kind of similar happening here. So if we say the solution is r to the n and plug it in, we end up getting this, r to the n plugged in. Well, we won't get this exactly, but if we plug r to the n in here for a sub n, so let me just write a sub n equals r to the n, then we end up plugging this into this recurrence relation is r to the n plus alpha times r to the n minus 1 plus beta r to the n minus 2 equals 0. Now, of course, you can factor out r to the n minus 2 here, and then you end up with r to the, well, I guess it'd be r to the second, plus alpha times r plus beta equals 0. Now, r equals 0 is a solution here, but if a sub n is 0, that doesn't really do anything for us. So instead we look when this is 0, and I'm just writing exactly that, only with x's instead of r's. So that's kind of where that comes from. I know it's a little deep and kind of complicated, but that's where this comes from, just so we know I'm not, we're not just making this up. I mean, it's a little left field, but it's not super unimaginable where it comes from. In other words, there is some explanation that is kind of near us. So anyways, I'm going to erase this now, and on the next board we'll actually see an example. Okay, so here I'm going to attempt to do these 2 examples, just demonstrating the characteristic root technique that we saw on the previous screen. I'm not going to actually generate the lists or even check my answer. I'll leave it up to you to check that and verify those things. But I'm just going to demonstrate the technique here. So the first thing to do is move everything to one side so the 0 is on the other. So we get a sub n minus 7an minus 1 plus 10a sub n minus 2 is equal to 0. The characteristic equation is then x squared minus 7x plus 10. Notice alpha and beta here, negative 7 and 10 respectively. That's pretty easy to solve. We can just factor the 2 things and multiply to positive 10 and then add to negative 7 or negative 5 and negative 2. So then this factors as x minus 5 times x minus 2. So then when you set each of them equal to 0, you get x is equal to either positive 2 or positive 5. So these are the distinct roots. They're different, right? So we're going to use the first version I explained, where you just take something times this to the n plus something else times this to the n. So I'm going to write that actually down here. We have a sub n is equal to a 2 to the n plus b 5 to the n. And now I'm going to attempt to be using these initial conditions one at a time. They'll give us an equation each, and then we can solve that system of equations then. Okay, so when n is equal to 0, we get a0 is equal to 2 a to the 0 plus b 5 to the 0. But since 2 to the 0, 5 to the 0 are 1, you just get a plus b on that side, and a0 is 2. So that just becomes this equation, actually. And similarly, when n is equal to 1, a sub 1 is equal to 3 on the left side. On the right side, 2 to the 1 is 2, 5 to the 1 is 5. So that's just simply 2a plus 5b. So that's not too bad. And in fact, now what I'm going to do is I'm going to actually erase some of this work here, if that's okay, which I'm sure you guys don't mind. And now let's solve this system. I'm going to notice that if you multiply this by 2, we get 2a plus 2b is equal to 4, just kind of rearranging things. This I'll leave the same, 2a plus 5b is equal to 3. I'll do bottom minus top, I guess. So those cancel out. Bottom minus top is 3b, bottom minus top is -1. So that b is equal to -1/3. Well, that's not that great, but okay, I guess it works. But since a plus b is equal to 2, let me write it over here now what happens. A plus b, which is -1/3, so a minus 1/3 really is equal to 2. So that a is equal to 2 plus 1/3. You can think of 2 as 6/3, right? 6 divided by 3 is 2 after all. So a is then 7/3. So that's our a value, that's our b value. We know what our form is, so this is our answer. But now we know a is 7/3. So 7/3 times 2 to the n, I'll write that in parentheses, minus 1/3 times 5 to the n, I'll write that 5 in parentheses, I guess. And again, I'll allow you to check that on your own to verify this works. So if you wanted to find a5, you can just plug in n equals 5. You don't have to jump through each of those steps and actually generate it and jump through a2, a3, a4, and a5. You can just plug it in, do some calculations, and you get a5. So that's the real benefit of closed form. You can just jump to the 100th term if you want. With these recurrence relations, you have to go from one to the next. It takes a while. Okay, so here, same idea. The recurrence relation set up in the way we want is a sub n minus a 6a sub n minus 1 plus 9a sub n minus 2 is equal to 0. Characteristic equation is x squared minus 6x plus 9. The two numbers are multiplied to 9 and add to -6 or -3 and -3. So this is actually -3 squared. So we actually get one solution that has multiplicity 2. In other words, we have a repeated solution. So R1 and R2 are both the same 3. So this is the second scenario. So here we get a sub n is equal to a 3 to the n plus b times n times 3 to the n. Okay? Now what we need to do is find out what a and b are. So if we let n equal 0, something kind of interesting happens that didn't happen above. Because of this n multiplied, that second term just goes away entirely, and we get a right away. So that's a0, which is 1 from the above, equals 3 times, or not 3 times, but a times 3 to the 0, which is just a. So that gives us a right away. And again, 0 times b times 3 to the 0 is just 0. So that second term goes away. When n is equal to 1, we get a sub 1 is equal to 4 on the left side. Here we get a times 3 to the 1, so it's 3a. Which we know a is 1, so that's just 3 actually. So I'll write that in a moment. Plus b times 1 times 3 to the 1. Right? N is equal to 1, we get that. Which is just 3b, by the way. So that's 3b. A is 1, so that 3 times 1 is 3. Subtract, we get 1 is equal to 3b. Divide, b is 1/3. Okay. Plugging those in, a is 1. Don't need that. B is 1/3. So there we go, and that is our answer, and now we can move on to one last example that you deserve to see. So let's take a look at that right now. All right, so finally, last example here, we have the most famous, or one of the most famous anyway, sequences in mathematics, the Fibonacci sequence. Just to remind you what that is, it's solving the recurrence relation, f sub n equals the sum of the previous two terms, where the first terms are 0 and 1. So if we start with 0 and 1 and add those two terms, we get 1. Add those two terms, we get 2. then 3, those two terms out to 5, those two terms out to 8, then 13, then 21, and on and on and on it goes. So, believe it or not, we can solve this recurrence relation, and it's just using the technique we saw. So I'm going to move everything to one side so that 0's on the other. Notice the numbers in front here are just 1 each, so the characteristic equation we get is actually pretty simple. It's x squared minus x minus 1. Okay? And solving this is actually pretty simple. I'll use quadratic formula though. I forgot equals 0. So quadratic formula, x is equal to negative b, so it's positive 1 here, plus or minus the square root of b squared, which is 1, minus 4 times a times c. So maybe I'll write that down just so we can see it, and it's all over 2a. So it says ax squared plus bx plus c is equal to 0. This is quadratic formula. Makes x equal negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. So that's what I'm using here. Here a, of course, is 1, so we have 1 here and 1 there. B is negative 1, so that makes negative b positive 1 here, and negative 1 squared is positive 1 there, and then we have that c, which is that negative 1. Now what this amounts to is actually 1 plus or minus the square root of, that's double negative 4, so it's positive 4 plus 1 is 5 over 2. Okay, now this actually has a pretty, I don't want to say important name, but this has a name in mathematics called the golden ratio. At least the positive version is called the golden ratio. The other one I think is called the inverse of the golden ratio. Maybe there is, I'm trying to think if there's a way we can kind of name that. Maybe I'll actually try to play with that after the fact. But let's call the positive one phi. So that's what the golden ratio is named after the Greek letter phi. So that's 1 plus radical 5 all over 2. Now the other one I want to kind of think about, I don't know why, but I have this hunch that it's actually the inverse. So let's take a look at 1 over phi. So 1 over phi is going to clearly be the reciprocal of this, but I'm going to kind of do this technique where we multiply top and bottom by the conjugate of the denominator. So we get 1 minus radical 5. Okay. Now, in the denominator, we get a difference in squares, which is 1 minus, I guess it's 1 squared minus 5, so it's 1 minus 5. So it's negative 4, actually. On the top, if you distribute, actually I won't distribute, I'll just leave it like that. So 1 minus radical 5 like this. Okay, so I mean, it's not terrible, but it's getting there. So what happens is we have negative 4 here in the bottom. And of course, 2 goes into 4 twice, but it's negative. So this is actually 1 minus radical 5 over negative 2, or we can write it as negative that over 2, which is negative the one we want. So what I can say is negative 1 over phi. So I was close. Negative 1 over phi is negative this, which is double negative that, which is positive that now, because the negatives now cancel. So one of them, the positive one, we call phi. The other one ends up being negative 1 over phi, as it turns out. Okay, great. So now what? Well, now all we have to do is write our kind of solution we had earlier. A sub n is equal to a phi to the n plus b, the other one, negative 1 over phi to the n. Okay, we border this off, doesn't get in our way. Now we can use our initial conditions. When n is equal to 0, a0 is 0. So we just get a plus b in that case, because anything to the 0 is 1. Okay, so that's fine. What about when n is equal to 1? When n is equal to 1, and by the way, this should be f sub n, not a sub n, because we're calling this f for Fibonacci, right? Now, if n is equal to 1, we get f1 is equal to 1. And then here we have a phi to the n minus b over phi to the n. Right, because negative 1 over phi to the 1, n is equal to 1 here, my mistake. Negative 1 over phi to the 1 is just negative 1 over phi times b is that. So actually we can solve for, can we solve for, I mean, maybe we can clear denominators by multiplying by phi here. So we get phi is equal to a times phi squared minus b. Oh, that's fantastic, because adding these, the b's cancel. So now adding these two equations here, the b's straight up cancel. So we get the following. Let me see if we can kind of rearrange some things. I'll tell you what, I'm going to erase some of the board and then we'll continue. Okay, so here is where we are with this problem. We found out the closed form is f sub n equals a times phi to the n plus b times negative 1 over phi to the n, where phi is given by this. And we ended up also finding out that negative 1 over phi is the conjugate of this. So maybe I'll write the negative 1 over phi is equal to 1 minus radical 5 all over 2, like that. And that's actually going to be kind of useful. And what we're going to do now is we're going to attempt to add these together. Notice when you add them, these cancel out. You get 1 times a plus phi squared times a. That ends up being 1 plus phi squared all times a is equal to phi. Perfect. But now solving for a, we get a is equal to phi over 1 plus phi squared. Now I was actually kind of struggling with this for a second. But then it occurred to me that if we divide the top and bottom here by phi, you end up getting 1 over phi plus phi, like that. And the magical thing here is that since negative 1 over phi and 1 over phi are conjugates, then 1 over phi and phi itself, they're not quite conjugates, but they're kind of like conjugates. Basically, the radical 5s will actually combine. In fact, you can kind of see that if you look at this, 1 over phi plus phi, the 1 over phi part is going to be negative this, which is negative 1 plus radical 5 all over 2, where the phi itself is going to be 1 plus radical 5 all over 2. So you get all over 2, the 1's cancel out, and you just get radical 5 plus radical 5 is 2 radical 5's, 2 radical 5, the 2's cancel, so you get just radical 5. So in fact, this is really just 1 over radical 5. Fantastic. And furthermore, from this original equation, if you solve for b, b is equal to negative 8. So combining that with our f sub n, we get the following. F sub n is equal to 1 over radical 5 times phi to the n plus negative 1 over radical 5, because b is negative 8, times that. So I'm going to write it like this. Phi to the n plus negative 1 over phi, its conjugate to the n, all over the square root of 5. Awesome. So there we go. We have the generalization, general closed form for the Fibonacci sequence. Fantastic. So if you wanted to find the 0, 1, 2, 3, 4, 5, 6, let's say 7th one, good luck, because taking that thing to the 7th is going to take a lot of effort. It's not super bad, because notice that since phi satisfies x squared minus x minus 1 equals 0, then that means phi squared minus phi minus 1 is also equal to 0, so that phi to the 2nd is equal to phi plus 1. So adding 1 to phi gives you phi squared. So if you wanted to multiply phi squared to phi squared, for example, to get phi to the 4th, it would just be phi plus 1 to the 2nd, which, for example, is phi squared plus 2 phi plus 1. But then phi squared, again, is phi plus 1, so you get phi plus 1 plus 2 phi plus 1. So altogether, that's 2 phi plus 2. So that's an example of finding phi to the 4th, just using the iteration of phi squared equaling phi plus 1. And you can do something kind of similar, actually repeat this process a little bit to find phi to the 7th. And its inverse is going to be, or its not reciprocal, but its conjugate, negative 1 over phi. It's going to be a little harder to find that to the 7th, but it's very similar, actually. Yeah, and then you'll find out that the radical 5s will somehow kind of group together in the top and cancel out when you divide by radical 5. So you should get 13, actually, if you try that. It'd be a nice challenge if you wanted to try that on your own. But I'm not going to, like I said, that actually concludes our discussion on solving recurrence relations. So I really hope you all enjoyed it. It was a little bit of a doozy, but there it is. And with that being said, thank you all for watching. I'll see you in the next video.